Hey, today our topic is graphing linear inequalities in one variable. Our essential question is, how do I graph the solutions of a linear inequality in one variable? So just a reminder for your notes. When we talk about graphing the solutions, we're referring to the ordered pair, or in this case, multiple ordered pairs that would make the linear inequality true. So for a reminder of that, you can go back to the previous lesson where we checked to see if an ordered pair was a solution to the linear inequality or not. When we graph linear inequalities, we're looking at graphing the solutions on the entire coordinate plane. So what I'd like you to do is pause the video and think about which ordered pairs are solutions to this linear inequality that x is greater than or equal to 2. In other words, which of these ordered pairs, these points on the graph, would be solutions to x is greater than or equal to 2. If we check each one, each ordered pair, we have to first start by identifying the coordinates of each point. And for this, yes, each coordinate or each ordered pair has an x and a y coordinate. However, we're only concerned with the x coordinate because that's what our linear inequality has in it, just the x value. So if we look at this first one on the left, we can see it's above the origin. So yeah, the coordinates would be 0, 1, 2, 3, 4, but the x coordinate is 0. Is 0 greater than or equal to 2? Well, no, it's not. 0 is not greater than 2 and certainly not equal to 2. So this is not a solution. If we check the next ordered pair, the next point as we move across from left to right, this one would have an x coordinate of 1 and a y coordinate of 6. The ordered pair is at 1, 6. So if we want to check to see if that's a solution, we take the x coordinate of 1 and test to see if that is true. Is 1 greater than or equal to 2? Well, it's not greater than or equal to 2 either. 1 isn't greater than 2, 1 isn't equal to 2. So that ordered pair also is not a solution. Next, as we move left to right, we see that we have an ordered pair at 2, 2. The x coordinate's 2, the y coordinate's 2. So let's check and see if that's a solution to our inequality. When we substitute the x coordinate, we get 2 is greater than or equal to 2. Well, let's see. I have two numbers that are the same, but is that a solution to my inequality? Is 2 greater than 2, or is 2 equal to 2? Yes, because 2 is equal to 2. So this is, in fact, a solution. And as we keep moving across from left to right, the next ordered pair would be at an x coordinate of 3, y coordinate of 4, 3, 4. So if the x coordinate is 3, substitute that into our inequality. Is 3 greater than 2, or is 3 equal to 2? Yes, it is, because 3 is greater than 2. This would represent a solution. And as we continue to check the other ones, you might notice a pattern developing that as you move to the right, the x value continues to keep getting bigger. For example, the next ordered pair is at 4, 5. So is 4 greater than or equal to 2? Yes, it is. The next one has an x coordinate of 5. It's 5, 1. Is 5 greater than or equal to 2? Yes, it is. And then last, we have an ordered pair at 6, let's see, 1, 2, 3. With the x coordinate of 6. Is 6 greater than or equal to 2? Well, yes, it is. And if you look at this carefully, you'll notice that the first time where we had a solution as we worked from left to right was when we had an x coordinate of 2. And in fact, any ordered pair that might be on that, I guess, vertical line where the x coordinate is going to be 2 would be a solution. And so would any of the x coordinates of 3, any of the points that have x coordinate of 4 or 5 or 6 or 7 or 8. I think you get the picture. Basically, anything to the right of this boundary. Anything to the left is not a solution because those x-coordinates are less than 2. We would only include the ordered pairs in which your x-coordinate is greater than 2 or equal to 2. So how do we graph this without testing every single ordered pair? There's a faster, easier way of doing this. And here's our 3 steps. First, we graph the boundary line at the corresponding equation. So in our example that we just looked at, x is greater than or equal to 2, we would want to graph a boundary line at x equals 2. You might recall from earlier this year, I believe it was Unit 1, where we graph linear equations with just one variable. And if we're graphing the equation x equals 2, we are literally looking for the line, in this case a vertical line, where all of the x coordinates are exactly 2. Like 2, 0, 2, 1, 2, 2, 2, 3. All of these ordered pairs have an x coordinate of 2. Therefore, they would be solutions to the equation x equals 2, as would any other point along that exact same line. Now, in step number 2, it tells us that there are actually 2 different types of lines that we might draw. There is a solid line, which you can see the example right there of what that looks like. It's just a regular line. And we use a solid line if the inequality symbol has the or equal to underneath it. Essentially, it's like representing a closed circle when you draw inequalities on a number line. The closed circle represented that the boundary value, the boundary number, did represent a solution. But in this case, because the boundary is not just a single number, it's a line, we want to represent a closed or filled in line to show the boundary. Now, if the inequality would have been a strict inequality without the or equal to bar underneath it, we would draw what we call a dashed line, and that would look like this one that I just circled. And that would be, again, if you have just less than, or if it's just greater than, but not equal to, then we would use a dashed line. And that'll be true as we graph linear inequalities all week. We'll be using that same concept here. It's a solid line if it has the or equal to part, and we draw a dashed line if it's not equal to. Now, for number 3 or step 3, it tells us to shade the half plane that contains all of the solutions. And you remember over here, we showed that all of the solutions are these ordered pairs that have x coordinates bigger than 2. Basically, anything to the right of the boundary line. And what we have on our inequality in one variable is anything to the right of this boundary line is going to represent a solution. Now, it's not just the ordered pairs that have x coordinates of whole numbers like 2, 3, 4, 5, 6, 7, and 8. But what about those x coordinates like, I don't know, let's say 4.5. 1, 2, 3, 4. So what about these? All of these x coordinates, or I should say ordered pairs, where the x coordinate is 4.5 and the y value can really be anything. Those are still solutions to this inequality, this linear inequality. So we want to include all the solutions, not just the ones that appear at the intersections of the grid lines. So to show all of the solutions, we simply shade the half plane, the entire right-hand side of that line. So we're going to take a look at just a couple of other examples before you get started on your homework today. So here's our next example. Number 1 says y is less than or equal to -2. Remember that inequality symbol is pointing to the left side. The pointy side is to the left, so that's our less than symbol. So less than or equal to. So if we follow our 3 steps, we want to start by graphing the boundary. The boundary is going to be at the equation y equals -2. So this time I want to know where are all of the ordered pairs that have a y coordinate of -2. Well, that's going to line up alongside the y-axis or I should say going through the y-axis at -2. All of those ordered pairs have a y-coordinate of -2, and the x-coordinate is the one that changes. So it's going to be a boundary line that goes through the y-axis right at -2 and extends all the way across. Now, looking at our inequality symbol, we have to try to remember if we draw a solid or a dashed line. Because we have the or equal to part here, we do want to include everything on that boundary as a solution. So we draw what we call a solid line, which represents that everything on that line also is a solution. The boundary includes solutions. So now which side do we shade? Well, if I'm looking for all the y values that are less than -2, think about your graph. You could even test a point. If you test a point up here, that's 2, 2, is the y coordinate less than or equal to -2? No, it's not. So that's not a solution. Test a point down below. X coordinate 2, y coordinate -4. Is the y coordinate less than or equal to -2? And this time it is. So all of the solutions are going to be on the half plane below the line, because that's where all of the y values will be less than -2. On the boundary line is where all the y values will equal -2. That's why we drew a solid line. For number 2, our last example, we're back to having an x in the inequality. X is less than 3. So let's start by finding the boundary. Where are all of the ordered pairs that have an x coordinate of 3? In other words, 3 comma something. Well, we have 3 comma 0, 3 comma 1, 3 comma 2, 3 comma 3. And so basically it's forming this vertical line that goes through the x-axis right at a value of 3. Before we draw our boundary, we have to check to see what type of line to draw. Notice this inequality does not have the equals bar underneath it, which means that the boundary itself does not contain any solutions, because 3 is not a solution to this inequality. Yes, it represents a boundary, but the boundary is not a solution. So for that, we draw what we call a dashed line. Some like to call it a broken line, where it's just not whole, it's not filled in. It would have been like graphing inequalities on the number line, where you draw an open circle and then shade left or right to represent that the boundary is not a solution. So now we do have to think about where are all the x coordinates or x values that are less than 3. Well, anything less than 3 is going to be to its left, like 2, 1, 0, and so on. So what we want to do is shade the half plane that contains the solution. Solutions, plural. Remember that line that we drew is the boundary that splits all the solutions from all the non-solutions. So now we just want to shade in the left-hand side of that boundary line to show all the solutions are on the left side. And it doesn't have to be perfect. You don't have to fill in every square inch, but if you can, just try to make it very clear and show where those solutions are.